Hello, I'm Ginger Pan, and you can find out my academic background by typing my name Ginger Pan into Google. Today I'm going to talk about beam theory, and I'm going to focus on one particular part of beam theory, that is this I here, this second moment of the cross-sectional area. And here is a small section of the beam, and we apply a bending moment. So if you apply a bending moment there, and then you can calculate the stresses on this cross section. And that y there, so is defined here. So this is a neutral axis. So y sit on original y sit on the neutral plane, and then it's going upward. So this I, we are talking about this second moment of the area. So the area we're talking about are that area. Yeah. Second moment of this area about this neutral axis. So that's defined by this equation, mathematical equation, y squared integration over dA integrated over this cross-sectional area. You say all that, it's hard to make sense out of what I've just said, yeah? What I'm talking about, second moment area. What does that mean? So this is the purpose of my presentation today. I want to explain, I want to give you a feeling of the meaning of all this. So I want to give you a feeling of that by going through a series of numerical examples. Normally, I don't like to play with numbers because we are understanding something, and numerical values sometimes they confuse you rather than help you. But in this particular case, I think it can help you. So bear with me. So I'm going to take you through some numerical examples. So that my purpose is to give you a feeling. Oh, and now I understand what all these things is all about. Okay. So I'm just considering a rectangular section there. So I just like the case I've explained. So for a rectangular cross section, like a beam, yeah. So let's say this is a beam. It's a very soft beam, and here we have a cross section. So that's the sort of section I try to draw there, not to the aspect ratio, but nevertheless. And we know for a rectangular cross section, if you do this integration, I'm not going to do it, you can do that yourself, or you can find a textbook. And the I can be calculated as BDQ over 12. So what is B? What is D? Yeah, BDQ over 12, but what is B? What is D? Is that B or is that D? So that's what I'm going to help you to clarify. Okay, so considering that fraction, I'll give you some numbers. So let's say that's 200 millimeter, and that's 100 millimeter. So let's sort of, I'm drawing this case again here, so I'm going to compare different cases. So that my first case is just this second. Now let's consider two different scenarios. In one case, this beam, just like that beam there, it bended in that way, yeah? So the beam bent in that direction. So I'm calculating this I, the second moment of the area, of this area, about this neutral plane, N. And if you do that, so that's what I'm doing here, I, N, using that equation, then this will be B, that will be D. Yeah? So that's B, that's D. So 1 over 12, 200 times D power of 3, 100 power of 3, and you end up with this number here. Nothing interesting so far. But then what I can do is, I can, I use a beam, but this time I flip it 90 degrees by 90 degrees, yeah? So now I'm using the beam in this way instead of this way, yeah? So instead of doing that, I'm doing this, flipping. So I'm talking about now I use MM is my neutral plane. So the beam is beam bends about So I calculate I use that equation. This time, this is B, this is D. Yeah, look at that equation, BDQ over 12. So this is B, this is D. So you do 1 over 12, 100 times 200 power 3. So these two change places, two numbers swap places. And you can do that calculation yourself, it's a simple calculation. So you end up with a value which is 4 times bigger than that value there. So I do 4 times that. Yeah, 4 times that. So what I mean is, in this case, you can bend that way, and if you flip, you bend that way, the I value changes, become 4 times bigger. Yeah, so that's obvious, isn't it? Yeah, so this is small. You flip it, it becomes 4 times bigger. So if this is 4 times bigger, the stress is 4 times smaller. Okay, so that's it's inversely proportional to I. So if this is larger, this becomes smaller. The stress becomes smaller. So this second case, yeah. So repeat. That way. If you bend it that way, if you flip it, and the stress becomes 4 times smaller. Right? So that gives me some understanding of what this I is about. It's a property of this cross-section, but it depends on which way you use your beam. So we understand it by looking at the beam, but numerically it comes out that way. So that's my first case. Yeah. My second case is that I'm going to expand it, so make this dimension 3 times bigger. So instead of 100, I make that 300. So you can imagine there's 3 of them there. Yeah, but this is a solid beam, so I'm not just putting 3 beams on top of each other. I make a solid cross section. Yeah, that's 3 times bigger. So let's do the same calculation again. So let's say first I let the beam bend, about NN, and then I let the beam bend about MM. So let's look at the beam bending about NN. So what I have is INN. Again, I use that equation. So NN bending our way. So that's my B, and that's my B. Right? So B is 200 times 300 power of 3, 300 power of 3. And you do that calculation, you end up with this is 27 times larger than this case. Yeah? So if this beam bend this way, and this beam bend this way, you use 3 times more material, but you reduce the stress by 27 times. So that's a big difference, right? But if I'm using my beam in that direction, and you can argue, and that is simply if I can draw this 3 section there. So if the beam bend about MM, this is just effectively 3 of this. Yeah, because each individual one still bend about the same neutral plane. So in that case, IMM is just 3 times that, and which is 12 times of this case. Right? The difference between this one and the previous one, when we have the beam bending about that direction, is because by making this a solid cross-section, you force the whole beam deform about this neutral plane, rather than each of them bending, deform about their own neutral plane. Right? So the I value about NN is much bigger than 3 individual beams bending about its own neutral plane. And that's make a big difference. It's 27 times bigger. Okay? So that's this case there. Yeah, that case there, that case there. Now let's look at the third case. And what I've done is I use three of these, but again, use three of these. I made an I section. Yeah, I made an I section. So again, it's not separate section. So this is the whole solid section. Yeah. So, but the amount of material you use, the volume of material you use in this case, is exactly the same as this case, and is 3 times larger than this case. So let's look at let's look at the neutral axis and again. Remember, in this case, the whole section is forced to bend about this neutral plane. So you can do this integration. You can calculate this by integrating. Do this integration. I'm not going to do that, but you can take a shortcut. You can argue that you can do this argument. You can say this section is the outside section minus take away this 2 bit. Yeah, so the I of the whole of this I section is the I section of the outer box minus this 2 empty box there. So what you can end up with, whichever way you calculate, you can end up with 60 times larger than that. So if in this case, just let me repeat again, this I section, the bending second moment of inertia about this and this is 60 times, 6 times larger than this case. But you are only using 3 times more material. Yeah, this is the volume of this, the material, the amount of volume you use for this case is only 3 times more of this. But the second moment of this I section about this neutral axis is 60 times larger than that, which means the stress will be 6 times smaller. So that makes a huge difference. Of course, you can do another calculation, the bending moment, the second moment about there, about that section. Then again, you basically that's 3 separate beams. That's 1, and another one there, and another one there, because each, they keep their neutral axis that way, so it will be 2 of those plus 1 of that. You can do that calculation, you end up with 9 times bigger than this. Yeah, so if the beam bend that way, the I value will be 9 times bigger with that. Okay, so here's a point I'm making. So how to use your material in beam, how to design your cross section make a huge difference. Yeah. See that? This case is you're only using 3 times more material, but by using this I section, you can reduce the stress 60 times. Right? So I'm going to demonstrate that, in this case. Yeah. So this is a very floppy material. This is something I get from my kitchen. Yeah. It's very soft. Yeah. And let me demonstrate. So imagine this is that case there. So it's floppy, and I use that and made an I beam myself. I just literally glue them together. I didn't make it. You see how strong this is now. This is a reasonable beam. It's very. You see that's very floppy, very soft. And look at that. Yeah, this is a solid. Yeah. So that's a 60 times different. Yeah, what this means. So now let's come back to this mathematical equation, this integration. I said it's quite hard to imagine what it means. To make I bigger, Now you think of that equation, what you need to do is to put materials away from this neutral axis. Yeah, this is a neutral plane. So what do you want to do in order to make that integration bigger? You want to put the material far away from this axis. Yeah? So a solid cross-section is not a good idea because you got equal amount of material everywhere. Yeah? So that's what you need to do to make I larger. So that's how you design a beam. You want to put your material away from the neutral axis. And we know why, because we know that when we have a beam, we apply bending moment, and the stress is tensile here, compression here, and the stress is large at the top and lower there, but there's not much stress in the middle part of the section. So that's why you want to put, when this beam is on the bending, the stress here is high, stress here is high, tensile compression, but there is not much stress in the middle. So if you put a lot of material where stress is high, top and bottom, of course it makes perfect sense. Thank you.